Hello and welcome back to my crash course on chemical bonding, part 2 of the crash course. So I'll start off by describing certain trends in bond strength and the explanation that you need to know for the H2 syllabus. So let's begin. The strength of a covalent bond can be measured by its bond energy, which is defined as the average energy absorbed when 1 mole of that bond is broken in the gaseous state. Generally, the stronger the covalent bond, the shorter the bond length. And factors affecting bond strength include the number of bonds, the effectiveness of overlap of the orbitals used to form the bonds, which depends in turn on the size of the orbitals and the hybridization of the orbitals, and thirdly, the bond polarity, which is the electronegativity difference between the two atoms forming the bond. So let us first take a look at the first factor, the number of bonds. So as you can see, from the C single bond C to C triple bond C, the bond energy increases. This is to be expected because there is a greater electron density in the internuclear region in the C triple bond C, thus greater electrostatic attraction between the shared electrons and the two nuclei, thus resulting in a stronger bond. But note that the bond energy of C double bond C is less than twice that of C single bond C. This is because the second pi bond in C double bond C is weaker than the single sigma bond in C single bond C. So the reason for this is because the side-to-side overlap in the pi orbit in the pi bond, right, is less effective than the head-on overlap in the C sigma bond C. So let us now take a look at how size of orbitals affect the strength of the covalent bond. So now we are comparing the Cl-Cl single bond with the Br-Br single bond and the I-I single bond. So we note that moving from Cl2 to I2, the strength of the homonuclear bond actually decreases. So this is because the size of the valence orbitals used in bonding increases from Cl to I, and larger orbitals are more diffuse, resulting in less effective orbital overlap in the bonds formed with larger atoms. Now let us take a look at the effect of hybridization. So let us take a look at the following molecules: ethane, ethene, and ethine. So the hybrid orbital of C used in the CH bond, you are looking at the CH bond here, is a sp3 orbital for ethane, an sp2 orbital for ethene, and an sp orbital of ethine. And we also observe that the CH bond energy increases. That means the bond increases in strength. The CH bond increases in strength from ethane to ethine. So the way to explain this is that moving from ethane to ethine, there is increasing S character of the carbon orbital used to form the CH bond. And the higher the S character, the less diffuse the hybrid orbital, since we know that the S orbital is more compact and less diffuse than the p orbital of the same quantum shell. And so the more effective the overlap with the orbital of the other atom, in this case the 1s orbital of the hydrogen atom, and the stronger the bond and thus the shorter the bond length. Let us now take a look at yet another factor affecting the bond strength, which is bond polarity. Moving from the NH bond to the FH bond, we observe that the bond strength increases as the electronegativity difference between the two atoms increases. So when electronegativity difference in the two atoms increases, the bond becomes more polar. There's a greater partial positive charge on the less electronegative atom and a greater partial negative charge on the more electronegative atom. And as a result, the attraction between these partial charges gives the bond a partial ionic character, and this electrostatic attraction between the partial charges strengthens the bond. Now let us take a look at polar bonds and polar molecules. So once again, I would like to bring to mind the ionic covalent spectrum. Right, so now we are looking at the center part of the spectrum, which is covalent bonds, but they are polar in nature. That means they have partial ionic character. So let us take a look at the polar covalent bond. The polarity of a bond is determined by the bond dipole moment, which depends on the magnitude of the partial charges and the bond length. the greater the electronegativity difference between the two atoms, the greater the dipole moment in general. And when there are partial charges, electrostatics can come into play, resulting in interesting properties. So this arrow over here, you may have seen before, represents the dipole moment. It points to the more electronegative atom. So you can think of it as the arrow points in the direction that the electron has moved, because the electron moves closer to the more electronegative atom. Another way to think of it is that this plus sign lies on the atom bearing the partial positive charge. So a dipole moment is a vector that has both magnitude and direction. So a molecule can have polar bonds but be non-polar overall. For example, carbon dioxide is a very good example. The dipole moments of the two C double bond O bonds are equal and opposite in direction, since the two C double bond O bonds are equivalent. And the geometry of the molecule is linear. The overall dipole moment of the carbon dioxide molecule is thus 0. There are other examples of non-polar molecule with polar bonds. And these are molecules that have 4 identical bonds arranged tetrahedrally, 3 identical bonds arranged in a trigonal planar arrangement, 5 equivalent bonds arranged in a trigonal bipyramidal arrangement, 4 bonds and 2 lone pairs such that the 4 bonds are arranged in a square planar arrangement, and 6 covalent bonds arranged in an octahedral arrangement. So now let us take a look at intermolecular forces of attraction. All intermolecular forces are electrostatic in origin. That is, they arise due to the attraction of opposite charges. The stronger the intermolecular forces, the higher the melting and boiling points, as phase changes of simple covalent compounds involve the breaking of intermolecular forces. There are 3 main types of intermolecular forces: ID-ID, PD-PD, and hydrogen bonding. So let us first take a look at ID-ID. It is the only type of intermolecular forces that exists between non-polar molecules which have no permanent dipole moment. So electrons are constantly moving in an atom. At any given moment, the electron density of a particle can become unsymmetrical, resulting in an instantaneous dipole forming on one of the molecule. So this dipole induces a dipole in the neighboring particle, because the presence of this instantaneous dipole means there's a partial positive charge on this end and a partial negative charge on this end, since electrons have moved in this direction represented by the arrow. So this attracts the electron cloud of a second neighboring particle, causing it to be polarized. This is called the induced dipole. And there's this attractive force between the partial positive charge on one of the instantaneous dipole and the partial negative charge of the induced dipole. So ID-ID interactions tend to be weak. They are short-lived as the electrons keep moving and the dipoles keep vanishing and reforming. And ID-ID interactions are present between all particles. So there are 2 main factors affecting the strength of ID-ID interactions. Firstly is the number of electrons, or the electron cloud size, and secondly is the surface area for interaction. So let us take a look at the first factor, which is the number of electrons, or the electron cloud size. The larger the electron cloud, the more easily they are to be polarized compared to smaller electron clouds. Thus, the strength of ID-ID interactions increases with the number of electrons in a molecule. So moving from F2 to Br2, the number of electrons increases, resulting in stronger ID-ID interactions, resulting in a higher boiling point, as the stronger ID-ID interactions require more thermal energy to overcome. Let us now take a look at surface area for interaction. For different molecules with the same number of electrons, ID-ID interactions are stronger in molecules with greater surface area for molecular interactions. Moving from pentane to 2,2-dimethylpropane, note that the chain becomes more and more branched, but all these are isomers. That means they have the same total number of electrons. But as the chain becomes more and more branched, the molecule has lesser and lesser surface area for interaction, resulting in weaker ID-ID interactions and thus decreasing boiling point. Let us now take a look at PD-PD interactions. Polar molecules have permanent dipoles resulting in partial charges. The electrostatic attraction between the partially positive end of one molecule and the partially negative end of another molecule gives rise to PD-PD interactions. Note that although carbon dioxide has polar bonds, it does not experience PD-PD interactions, as overall it is a non-polar molecule. The bond dipole moments cancel out to give an overall dipole moment of 0. PD-PD interactions only exist between molecules with an overall molecular dipole moment. For molecules with a similar number of electrons, those with PD-PD interactions tend to have higher boiling points than those with only ID-ID. For example, ICl, a polar molecule, has a higher boiling point than Br2, a non-polar molecule, as the PD-PD interaction between ICl molecules are stronger than the ID-ID interactions between Br2 molecules. So the strength of PD-PD interactions increases with increasing dipole moments. However, for molecules with vastly differing number of electrons, we note that ID-ID interactions may become stronger than PD-PD interactions. So the ID-ID interactions between Br2 molecules is stronger in fact than the PD-PD interactions between polar ClF molecules, because Br2 simply has more electrons, resulting in an stronger ID-ID interactions. So now let us take a look at the third kind of intermolecular forces, which is hydrogen bonding. A very strong PD-PD interaction occurs between molecules containing a H atom bonded to a very small and electronegative atom with lone pairs. In our syllabus, you'll be learning that this other atom can either be a fluorine, an oxygen, or a nitrogen atom. So the highly electronegative FO or N atom causes the hydrogen atom bonded to it to have a high partial positive charge, allowing it to interact strongly with a lone pair on another FO or N atom. So example of hydrogen bonding can occur between two molecules that are from the same compound, or between two molecules of different compounds, for example a HF and a H2O. So for molecules with similar number of electrons, hydrogen bonding tends to be stronger than PD-PD interactions, which tend to be stronger than ID-ID interactions. So what factors affect hydrogen bonding strength? So we do observe that water has a higher boiling point than ammonia. Why is this so? This is because if you have 100 molecules of ammonia and 100 molecules of water, there are 100 lone pairs on ammonia molecules, 300 partially positive hydrogen in the 100 molecules of ammonia, but the number of lone pairs is limiting. Hence, the total number of hydrogen bonds formed between the ammonia molecules is 100, resulting in only one hydrogen bond formed per molecule. However, for 100 molecules of water, there are 200 lone pairs on the oxygens, 200 partially positive hydrogen atoms in the water molecules, resulting in a total formation of 200 hydrogen bonds between the water molecules, resulting in average of 2 hydrogen bonds formed per molecule. So we say that there is a more extensive hydrogen bonding network in water than in ammonia, resulting in stronger hydrogen bonding interactions and a higher boiling point. So how do we predict solubility using intermolecular forces? So when a solute X is dissolved in a solvent Y, there are few processes which occur. Firstly, the intermolecular forces between the molecules of X are broken in an endothermic process. The intermolecular forces between molecules of Y are disrupted as we push molecules of Y apart from each other to make space to dissolve molecules of solid X within it. This process is also endothermic. And intermolecular forces are formed between molecules of Y and molecules of X in an exothermic process. So we say that X will be soluble in Y if the energy released from forming the intermolecular forces between X and Y outweighs the energy absorbed in breaking the intermolecular forces between molecules of X and between molecules of Y. So let us take a look at two examples: dissolving iodine in hexane and dissolving iodine in water. So when we dissolve iodine in hexane, right, we are overcoming ID-ID interactions between the iodine molecules, and disrupting ID-ID interactions between the hexane molecules. And you are forming ID-ID interaction between iodine and hexane molecules. Overall, this works out to be favorable. However, when we dissolve iodine in water, okay, we are overcoming ID-ID interaction between iodine molecules. We are disrupting hydrogen bonding between water molecules. And we are forming ID-ID interaction between iodine and water molecules. But note that the formation of weak ID-ID interaction between iodine and water molecules does not outweigh the energy absorbed in disrupting the strong hydrogen bonding between water molecules. So overall, the process will be endothermic, and thus dissolution will not be favorable. So we can thus deduce the very common rule that I'm sure that you have heard of, which is like dissolves like. So now let us take a look at the second last part of our topic, which is lattices of crystalline solids. So the physical properties of a substance are consequence of the structure and the bonding. High melting point means strong bonding between the particles. Low melting point means weak interaction between the particles. Ability to conduct electricity means the presence of mobile charge carriers. So let us take a look at the ionic lattice. Ions are held in fixed position in an orderly arrangement by ionic bonds, right? Which is basically the electrostatic attraction between oppositely charged ions. So ionic bonds are usually strong and a lot of energy is required to break them. The strength of an ionic bond is determined by the lattice energy, which is defined as the energy released when 1 mole of an ionic crystalline solid is formed from its constituent gaseous ions. For example, if the energy released when we are to form 1 mole of NaCl solid from 1 mole of Na plus gaseous cations and 1 mole of Cl minus gaseous anions. So the larger the charges, the greater the lattice energy, right? Because the stronger the oppositely charged ions attract each other. The smaller the distance between the charges, the greater the lattice energy, as the oppositely charged ions can come closer together for interaction. And the greater the magnitude of the lattice energy, the stronger the ionic bond. So we can thus express lattice energy to be proportional to the product of the charges of the ions divided by the sum of the radii of the ions. So this formula is actually derived based on Coulomb's law, which is a physics electrostatics law, right? So thus qualitatively, strength of an ionic bond is favored by higher charge on the ions and smaller radius or size of the ions. So we can easily see that comparing between NaF and NaCl, NaF will have the stronger ionic bond because the F minus anion is smaller in size than the Cl minus anion. Comparing NaF and MgF2 on the other hand, MgF2 will have a stronger ionic bond as Mg2 plus has a higher charge than Na plus. So these are some physical properties of ionic compounds. You probably have learned this in secondary school already. So the key point to note is high melting and boiling points, because melting and boiling requires the breaking of strong ionic bonds. You can think of it this way: melting a substance requires the breakdown of the rigidity of the structure, and in order to break down the rigidity of an ionic structure, we have to break strong ionic bonds. So now let us take a look at giant molecular lattices. A solid with a giant molecular lattice structure is made up of atoms held together in an extensive network made up by covalent bonds. Such solids are said to have giant covalent structures. So an example is diamond, where each carbon atom is covalently bonded to 4 other carbon atoms arranged tetrahedrally around it. So this bonding pattern extends infinitely throughout a crystal of diamond. So the resultant structure is extremely strong and rigid. So melting and boiling, which is removing the rigidity of the structure, now requires breaking of strong covalent bonds. Thus, diamond has a high melting and boiling point. Dissolution also requires the breaking of strong carbon-carbon bonds, which are not compensated by weak solvent-solute interactions. And it is an electrical insulator, as all of the valence electrons of each carbon atoms are involved in forming 4 covalent bonds per carbon atom. Thus, there are no delocalized electrons and no free mobile cations or anions that can act as charge carriers. Thus, it is an electrical insulator. But we'll soon see another example, which is graphite, right? In the structure of graphite, each carbon atom forms 3 covalent bonds with neighboring carbon atoms and has a lone pair of has an unpaired electron stored in a p orbital. And there's attraction between layers of graphite, which are ID-ID interactions. So due to strong covalent bonds in each layer, graphite has a very high melting point. Because to remove all the rigidity in graphite, we have to break the CC bonds, the covalent bonds which are extremely strong and difficult to break. However, there are weak ID-ID interaction between the graphite layers, allowing the layers to slide over each other. Thus, graphite is soft and can act as an industrial lubricant. We also observe that graphite is an electrical conductor. To understand why, we have to understand that each carbon atom has a single electron stored in a p orbital. So the p orbitals of all the carbon atoms can overlap, forming an extended pi electron cloud. So the pi electrons are said to be delocalized, that means no longer localized on every carbon atom, but spread out over the whole layer, such that graphite is an electrical conductor. Because these delocalized pi electrons can act as free mobile charge carriers to conduct electricity. But since the pi electrons are only delocalized within each layer, graphite can only conduct electricity in a direction parallel to the layers. So now let us take a look at the final lattice structure, the simple molecular lattice, which is formed in simple covalent compounds. So the atoms in each molecule is held together by strong covalent bonds, but the molecules are held together by weak intermolecular forces of attraction. So generally, there are low melting and boiling points because to remove the structure, the rigidity of the structure, which is to melt the substance, we can just break the intermolecular forces of attraction between the molecules and the structure will lose rigidity without breaking the strong covalent bonds within the molecules. And it's generally soluble in non-polar solvent, except for polar molecules, especially those capable of hydrogen bonding. They can be soluble in water as well. It's an electrical insulator in solid and molten state, but molecules that ionize in water can form free mobile charge carriers in solution, thus enabling it to conduct electricity in the aqueous state. Example of these molecules are the hydrogen halides. So now the last lattice, which is the metallic lattice. It is a rigid lattice of positive ions surrounded by a sea of delocalized electrons. The metallic bond is the electrostatic attraction between a lattice of positive ions and the delocalized electrons, and the metallic bonds are strong and non-directional. The strength of the metallic bond depends on the number of valence electrons available for bonding. So magnesium with 2 valence electrons available for bonding has stronger metallic bonds than sodium with 1 valence electron available for bonding. Next is the cationic size of the metal. The smaller the cationic size, the stronger is the metallic bonding, as a smaller cation has greater charge density and stronger attraction for the delocalized electrons. So sodium from period 3 has stronger metallic bonds than potassium from period 4, as Na plus has a smaller cationic size than K plus. So these are the physical properties of metals. So one key point is malleable and ductile, as the metallic bond is non-directional, allowing a layer of positive ions to slide over another easily without breaking the metallic bond. So now let us move on to the last but very important concept in our chemical bonding topic, which is resonance. There are some molecules which valence bond theory as a model appears to fail. One can draw 2 possible structures for benzene. Right, so the difference is the positions of the C double bonds. However, what this suggests is that benzene has 3 CC double bonds and 3 CC single bonds. But in reality, when we actually do a spectroscopic analysis of the benzene molecule, we realize that the 6 carbon-carbon bonds in benzene have the same length, which is an intermediate between a CC single bond and a CC double bond. It is as if the real structure of benzene is an average of the 2 structures we have drawn. So we take the average of the two structures to get a better model for benzene. And we draw an arrow between the two resonance structures, meaning we are taking the average of the two resonance structures to form the real structure of benzene. The two resonance structures do not exist in reality. The arrow does not indicate an equilibrium, nor does the arrow indicate that a single molecule flits back and forth between the two structures. So resonance is not an equilibrium between different states. It's not different states that a molecule alternates between, and the different resonance structures we draw do not exist in reality. For example, at no time does benzene have distinct double and single bonds. Reality is a weighted average of the resonance structures drawn. So other molecules that exhibit resonance includes ozone, where the ozone molecule is an average of these two resonance structures. Thus, the terminal oxygen atoms have a negative half charge, and each OO bond has partial double bond character. Similar for the carbonate anion, CO3 2-, right? Each terminal oxygen atom has a negative 2/3 charge, and each carbon-oxygen bond has a partial double bond character. So there are cases where one resonance structure actually contributes more to the true picture of the molecule than other resonance structure. But in these two cases, because all resonance structures are equivalent, they contribute equally to the eventual structure. So this brings me to the end of the chemical bonding topic. I hope that it has helped in your understanding, and do follow up for more future videos on H2 chemistry. Thank you.